Okay, welcome to the EOL seminar. It's my pleasure to introduce today's speaker, Professor Julie Lundquist from CU Boulder. Professor Lundquist did her bachelor's degree at Trinity University in San Antonio, Texas, and that was in English and physics. And then she came here to Boulder, to CU Boulder, and did her graduate studies there. After graduation, she spent some time at Lawrence Livermore National Lab in California, where she designed and led wind energy projects. And after that, she came back to Boulder, and where she has now a joint appointment at CU Boulder as an associate professor and at NREL. And so her expertise is a boundary layer, and with a special focus on wind energy. But she also she simulates wildfires, and one of her main interests is also flow in complex terrain, which we will hear about today from the Perdigäo field campaign that many of you were also involved in.
Thank you, Ricky, for the kind introduction, and thank you all for coming here this afternoon to spend some time with me. I know that many of you know Perdigäo very well, having spent a lot of time at that wonderful location. And so for those of you who were there, I hope that this is a fun opportunity to see a little bit of the results that we've discovered. And for those of you who weren't there, I hope that this intrigues you into exploring the data sets on your own and potentially learning more things. So I was really excited to have the invitation to come talk with you about some of the results that we've had for Perdigäo. So as you know, with any large field campaign, hundreds of people are involved in making it a success. And so I wanted to list at least a few of the people, primarily the University of Colorado students who worked with me most closely, but well as our colleagues from the University of Oklahoma, from the University of Notre Dame, from the German Aerospace Center, DLR, and of course here at EOL and the Army Research Laboratory. So obviously I couldn't list everyone's names here, but as you know, a lot of people went into making this a success. And of course, nothing happens without research funding, and the National Science Foundation was very critical in a lot of this work, and we had considerable help from the locals in the area. And I would very much like to talk about some of those fun experiences with locals if you'd like to ask me about that later. So for those of you who have not been exposed to the exciting experiment that happened in Portugal almost 3 years ago now, it's hard to believe, there's a beautiful video that you can find on YouTube. The link is here if you want to take a picture of it. You can also search for DTU, the Danish Technical University, and Perdigäo, and then the movie will come up. So other collaborators spent significant funding having this movie made, and I've used it in my classes. It's a very nicely done video. So for today's discussion, I'm going to quickly give a little bit of an overview of the Perdigäo campaign, and then I'm going to talk about 2 research projects that I've been involved with that are very focused on turbulence dissipation rate. This is one of my pet topics to think about. And so the first paper that I'll talk about was led by Nicola Bodini, one of my PhD students who has since graduated and is now a postdoc at NREL. And then the other one was led by Norman Wildman from DLR, and I actually spent part of my sabbatical at DLR working with Norman on this project. And then depending on questions and timing, I'll give a little bit of highlights of some of the large eddy simulations that Tina Chow and her students are working on, and then I'll talk about some upcoming work in my project. So for those of you who don't remember the long history of the Perdigäo campaign, it originally started as a project for the new European Wind Atlas. And so the idea was to collect some validation data for models that predict wind resources in areas all around Europe. So there were 6 or 7 experiments that were highlighted as part of NUA. But then Perdigäo, because it was in such interesting complex terrain, offered opportunities for us to think about flow in complex terrain and to think about more fundamental fluid dynamics. And so then a group of us got NSF funding so that we could participate in that and then supplement the existing NUA measurements with those from our own research groups. And then EOL was brought in and carried out really Herculean tasks in order to deploy meteorological towers and remote sensing instruments to support it. So the focus of Perdigäo is this double ridge in central Portugal. The ridges are about 1,500 meters apart, 1,400, 1,500 meters apart, and climatologically, the flow tends to be perpendicular to those ridges, which makes it kind of nice if you, well, we thought that it would be kind of nice if you wanted to simulate it in a wind tunnel. Interesting things occur, obviously, when you add a canopy to flow like this. The campaign itself occurred over a month and a half in 2017, but of course there were measurements that extended before and after that campaign with almost 200 sonic anemometers, an amazing number of remote sensing instruments, and then this is a list of participating universities. So when you look at this cover of BAMS that includes the Perdigäo overview picture, and that title, Finer Flows, do you think that they're actually referring to the condensation of the liquid nitrogen here? I'm always a little bit concerned when people look at that and like, oh, those are really fine flows. I'm like, no. That was just calibration for the radiometer. So we were looking more at flows that are like recirculations within this valley, not at millimeter or centimeter scale types of flows as you see there with, this is Matt from the University of Oklahoma calibrating a radiometer. Sometimes it's fun to have an exhaustive list of measurements, and some of you will remember the wall that was up on the operations center in Alvead with a list of all of the measurements and all of the variables that we had at the campaign. But the list is here for your amusement or distress, depending on how you feel about large data sets. And since I'm coming here to speak to NCAR people, including a lot of EOL people, I thought that it would be appropriate to include some fun pictures of engagement with the locals and enjoying local food, and the turbine that was located on one of the ridges. And that turbine ended up being very important for some of our studies of turbulence in complex terrain. And it was really nice that we had a row of towers, and I'll show you a map in a few moments, to let us sample flow coming off of the turbine, and in particular the turbine wake. So my usual audience has a lot of familiarity with wind energy, and I'm not sure that that's appropriate here. So can you raise your hand if you have a good sense of what characterizes a wind turbine wake? Okay, so it's a pretty small portion. So what I get excited about is the wind speed deficit that we see in a wind turbine wake, as well as the enhancement of turbulence that we see in a wind turbine wake. So those are the two things we're going to be looking at later. And the fact that the turbine was located on that ridge makes it really interesting to explore those phenomena. So some of you in the audience actually built this web page, but I wanted you to know that when I give general talks about Perdigäo, I always include this page, and I try to encourage other people to access the large amounts of data that we have archived there. All right, so the Perdigäo campaign is named for a small village that is just outside of the Cobrão Valley, but this is its location in central Portugal on the larger Iberian Peninsula. And if we zoom in, we can see that the terrain that we call complex terrain is really just here, these two very subtle ridges. And there is a lot of other more complex terrain that we have since understood to have a very large impact on the flow within the Perdigäo Valley. So there are several interesting papers that discuss the larger mesoscale situation during the experiment, and I would definitely encourage you to look at that. That's not my focus today. But the larger picture of the campaign was really focused on flows within this valley. So we want to think about how the terrain outside of this double ridge valley has modified the approaching flow, so we almost certainly do not have a nice log law profile approaching in. But we do have many cases where we have flow separation as it comes up and over the ridge. We have wind turbine wakes that are generated as soon as the winds 100 meters above this ridge, as soon as those winds are 3 or 4 meters per second, then we have wakes that are generated, and there's quite a debate right now about whether those wakes will follow the terrain or whether they will propagate up and over. And as I'll indicate later on, I am firmly in the camp that believes that in stable conditions, the data show that the wind turbine wake will follow the terrain, whereas in convective conditions, the wake ends up being lofted up and over. But this is one of the first really good experiments in complex terrain to help us understand the dynamics of the wind turbine wake. And here's the zoomed in version of the wake. So there are a lot of interesting topics that people have explored with the Perdigäo data set, and as I indicated before, I'm only really talking about 2 of them today. So I would encourage you to look at this ACP, or Atmospheric Chemistry and Physics, Atmospheric Measurement Techniques, and Wind Energy Science. 3 journals are doing a joint special issue, and that link can be found here. And I've listed just some of the interesting topics, but that's only a small subset of the topics that have already come out of this data set. Now, when I was a graduate student, I had the privilege of working with Peggy Lamone, and she had told me that she had done a study of how long it takes for the largest number of papers to come out after a field experiment. And I like talking to my students about this also. And it's tended to be 7 years at that time. So we're only 3 years past the conclusion of the Perdigäo campaign, so I'm positive that many more interesting papers will be coming out from this data set. Further, I understand that Robert Menke was here for 6 months and also gave an EOL seminar, so I think that he's probably talked to you guys about the circulations that he was able to see using LiDAR scans in Perdigäo. But those are some of the most exciting results that have come out so far. All right, so again, going back to Perdigäo's location within Portugal, and then kind of zooming in on a Google Earth view of the Double Ridge Valley. So one ridge is here, the other is there, and the tiny village of Perdigäo, which ended up not being a center of our activity during the campaign, is there. So these are the ridges and the wind turbine. And now these ridges are represented on a topographic map, and you can see the dots representing the locations of the towers that were set up to provide us with transects that I'll talk about in a little bit. But it's also exciting to see how much data we collected at how many altitudes. So this histogram on the right is telling us how many sonic anemometers were deployed at different heights throughout the 45-day campaign. So we had 3 sonics on 300-meter towers, as you see on the far right, and then we had a profusion of 60-meter and 40 and 30-meter towers as well. So we have a really good sense of we have really good data sets to quantify how turbulence behaved in and around this Double Ridge Valley. So here's another way to look at that development. And it's really nice to be able to contrast the measurements on the valley floor, which is what we see in green here, with the ridge tops in brown. So I'm going to be showing some differences later on about when we have flow that's decoupled within the valley and on the ridges. And it's really nice to have so much data to quantify that. So I believe that Vanda has asked me at a conference, how many towers are necessary? Like, was it absolutely necessary to have all 49 towers?
No, the question was about lidars.
Okay, well, I'll give you even more larger numbers for lidars, but but I was very careful to not have an answer because I think that there are things that we've learned from all of these individual towers and certainly from all of the individual lidars. But I'm really, as someone analyzing the data, I'm really pleased that we have such a profusion of data. So in addition to the ridge and the valley sites, we also have 2 transects. One of them focused on a gap in the terrain here. So the ridges were not perfect ridges. They actually had interesting features and complicated canopies. But the yellow one was the gap transect, and then the gray one sampled the wind turbine wake when the wind was exactly in the direction, when it was exactly southwesterly flow. This gray line should have sampled wind turbine wake. And then because my research group had both remote sensing instruments and lidars, and we also had in situ instruments, so I really like to show this picture, which shows off 2 of the EOL towers, the wind turbine, and then a helicite system with turbulence measurement probes that my group was flying from the center of the valley. The Army Research Lab was flying a similar system outside of the valley, so we could do a comparison and contrast. And just because I really like the wind turbine wake measurements, I wanted to contrast these 2 scans from DLR, and this work ended up being Stefan Kigle's master's thesis. And I want you to contrast what you see on the left with what you see on the right. The main difference is that on the left we have stably stratified conditions, and on the right we have convective conditions. And what we're looking for is, flow is coming from the left in both cases, and the colors indicate the radial wind speed from the LiDAR, which is sitting over here on this opposite ridge. So what we expect to see if we see a wake is an area of red or pink flow showing slower wind speeds coming towards the LiDAR. And here we actually have stronger wind speeds, and then there's actually a flow reversal aloft, which is why this is red here. But if you look at this long enough, or if you do a quantitative analysis, you will note that the wakes in stably stratified conditions are much longer and persist further than they do in convective conditions. And this makes sense because just like with smoke plumes, you would expect to have a distinct plume that holds its integrity longer in time and longer distance downwind than you would when you had strong convection like what you see on the right. Okay, so if you were hoping for an overview of Perdigäo, this concludes that portion of the presentation. And now I'd like to shift to talking about turbulence dissipation rate. And so, as I said before, this is work that Nicola led while he was a graduate student in my research group. And he got very interested in learning machine learning and applying that to better estimates of turbulence dissipation rate. So I realized that not everyone is as excited about this as I am. So just as a reminder, we have a budget of turbulent kinetic energy in the atmosphere. We don't often think too much about the storage term, but we can generate it mechanically, we can generate it or suppress it with buoyancy. Then we have the advection, turbulence transport, and pressure transport terms. But then to close the budget, we have to have a good understanding of turbulence dissipation. And this often gets parameterized in our mesoscale models. And in fact, that can be very important as we run models at higher and higher resolution. So we tend to have the assumption of local equilibrium within a given grid cell. We assume that whatever is generating turbulence, whether that's a wind turbine generating a wake or flow in complex terrain, we assume that that turbulence production is dissipated within the same cell. And this is probably fine if we're operating at 3-kilometer resolution. However, if we go down to 1-kilometer resolution, there's the opportunity, and we've seen this in urban areas, we see it with wind turbine wakes, we see it in complex terrain, we see that turbulence is produced and dissipated in different locations. And so as a result, we should probably improve our numerical models so that we can accommodate this mismatch. And we can see that this is really important if we care about different applications. So I do a lot of wind energy related work. And so I would like to point out 2 recent papers that have looked at the sensitivity of hub height wind speed. So this is a wind speed at the height of the wind turbine. And Yang et al. And colleagues at PNNL did a really nice study where they ran a bunch of simulations for mesoscale simulations for flow in the Columbia River Gorge region. So this is just a map. And the colors here tell you how much of the variability in wind speed was due just to the way that dissipation rate was parameterized. So this study, which focused on summertime flow, and the follow-up study, which focused on wintertime flow, this tells me that there's something really important about dissipation rate and that we should be paying a lot of attention to how we parameterize it. And of course, if you are interested in the wind energy application, if you don't get your prediction of hub height wind speed correct, then and the hub height wind speed would be here on the x-axis, then your prediction of power production, which is critically important for the stability of the power grid, small errors in wind speed prediction lead to very large errors in wind power production. So it's important to get this right. So Nicola's interests were in figuring out if machine learning can help us develop better representations of dissipation rate, because existing parameterizations were developed in the early 70s and they have been mostly robust so far, but now that we're challenging the models by going to finer and finer resolution, we probably should address that. So he calculated dissipation rate from the nearly 200 sonic anemometers at Perdigäo. He tried both just the simple inertial subrange approach, but ended up using some of Domingo's work to justify using the second order structure function method instead. And then tried to say, okay, well, the MYNN PBL scheme, so this is one of the most commonly used PBL schemes in models like WRF, basically says that dissipation is just a function of TKE and a length scale. And then he tried to predict that length scale and then challenged this particular model to see if it could predict what the observations showed. So the problem is with the data that we have from Perdigäo, we can't actually estimate the length scale for the buoyancy effect or the turbulence structure. So we just took the surface layer estimate, recognizing that this is going to cause us to overestimate the overall length scale, but that means that we're going to end up underestimating dissipation rate. Okay, so now I'm going to take the actual measurements of dissipation rate and compare them to what would have been predicted using these two numbers. And keep in mind that we're already underestimating dissipation rate. So we already see that even though we already have that built-in offset, we still have a pretty significant bias if we just trust the MYNN PBL scheme. So this means that we certainly have room for improvement, and then that bias would be even larger if we had all the appropriate length scales to use. So this is justification for going on and continuing to explore. We can compare how MYNN behaves in stable conditions and in unstable conditions because we have so much great data from Perdigäo. And we can see that MYNN performs worse in stable conditions with a alarmingly high bias. Keep in mind that these are very small values of dissipation rate, so the bias is influenced a little bit by that. And because we have so much data at Perdigäo, we can distinguish what's happening on the ridges. So only the towers highlighted in yellow here are shown on this distribution plot. And we can distinguish the ridges from the valley measurements as well. And can see that MYNN behaves worse in stable conditions and in the valley. Jim, you have a question?
Could you just say a little bit more about how you measure the dissipation rate and what assumptions go into your measurement and what approximations you use?
So we basically just use the method that is typically used from sonic anemometers. Back here, the second order structure function method. So we would like to be able to see this slope. We don't always see this perfect slope. And so that actually raises an important issue that we do have error quantification with this method, and I don't go into that at all in this talk. But depending on how much disagreement we have with this line, then we can quantify how much we trust our measurements. But that's not shown here. But that is certainly a good point. Okay.
Same point. When you're in stable conditions, how much of the total dissipation of energy is conductive dissipation? So you have a transfer of shear produced kinetic energy into both turbulent kinetic energy and turbulent potential energy, and that's smeared out by conductive dissipation.
Yeah, so we did not distinguish between those two different sources in this study, so I couldn't answer that right now. Okay, so stable is worse, valley situations are worse, and then if we look at the profiles that we have, based again on the large number of towers, we can see that the disagreement tends to be larger closer to the surface. So this might address a little bit of your point about conductivity. So the next stage is to say, okay, the existing parameterizations that we have now are not as useful as we would like them to be. And so Nicola wanted to experiment with machine learning. And so we made a list of the typical quantities that we would expect, TKE, and we're including TKE to the 3/2 as a separate variable. We know that there are issues with that, but we did that for a particular reason. We have U star, we have height, we have the Obuchov length, we have normalized Obuchov Z over L, and then we included this other parameter, the standard deviation of the terrain. And I'll get to that in 2 slides to explain how that works. So the idea is that we want to use all of these variables to try to predict what dissipation rate actually is. Because we're in a slightly complex terrain situation, we have the opportunity to think about the effects of topography. And so for each site, for each data point, to calculate this standard deviation of topography, we took the wind direction at that particular site, and then we took a 30-degree arc of the terrain, and extending out for a 1 kilometer radius. So at this particular location, we would have a relatively small standard deviation of height. But if we were on one of the ridgetop locations or even within the valley, because we're using a 1 kilometer radius, we would have a much larger variation. So we're trying to account for the complexity of the terrain. So we have a 6-week field campaign. So Nicola would pull out 1 week for testing, use the other 5 weeks for training, reshuffle, use a different week for testing, the other 5 weeks for training, so that every data point was used either for testing or for training at some point within the machine learning process. And so this is a rinse and repeat cycle. And so then the idea is to test different approaches for machine learning to quantify which one was the most useful one. So linear regression is clearly inadequate because we have this extremely large overestimate of what dissipation rate is when we are at small values of dissipation rate. And this is kind of interesting because this echoes back to some of the problems that we have that we'll talk about later on when we start to use lidars for estimating TKE dissipation rate, because there's a similar signal to noise problem there. As bad as this looks, it actually is a little bit of an improvement on MYNN, but that problem at the very small levels of dissipation is not adequate. He also tried polynomial regression and gets a much better distribution, again with a lower mean absolute error. It's a 20% improvement on MYNN, and most importantly, it eliminates the bias, and that was one of the things that we were trying to go for. I believe that his favorite approach ended up being the random forest method because that has an even smaller MAE and has no bias. So in the machine learning world, it's often interesting to look at which parameters are important and how they are important in predicting the quantity that you're focused on. So if you look at all the TKE variants, they're explaining almost 60% of what is happening with these predictions of dissipation rate. And then if you look at topography, it's only 6%. But I don't think that that's an argument for excluding topography from consideration. I think it's just interesting to note that at least in this data set, it was not a critical component. And if you look at the stability metrics, either U star or Obuchov length, then together they explain about 10% of the variation. So to summarize this part of the project, we can show using the Perdigäo data sets that MYNN's parameterization is not ideal in stable conditions or within the valley. And machine learning techniques are promising, but we still need to keep a focus on TKE, which is kind of satisfying because that was the basis of the existing parameterization in the MYNN scheme. So it's nice to understand that the machine learning results echo what we already know from 3 decades of experience with MYNN, that TKE is really important. Okay, so I would like to move on now to talk about retrieving dissipation rate from remote sensing instruments. And so this is continuing that same theme of worrying about the details of turbulence and thinking about new ways of assessing them. So these are the co-authors on the paper, and again, it was led by Norman Wildman at DLR. So we wanted to take advantage of all the instrumentation that was available at Perdigäo. So I've already talked quite a bit about the sonic anemometers on the tower, and I briefly mentioned the tethered lifting system that my group flew from within the valley. Let's see, where are we? We're right here. So this is the base of the tethered lifting system, the red diamond for the people looking online. And then the red squiggle is the GPS location of one particular night's flights of the tethered lifting system. We also had profiling lidars, WinCube V1s and V2s. We had a scanning lidar at the blue diamond. So that's located right there. And so we have a method that Nicola had actually developed as an earlier part of his thesis for quantifying dissipation rate from the vertically staring lidar. And then Norman was operating lidars at number 1 and number 3 and was able to use those to create virtual towers of these orange dots and then to make RHI slices across the valley. So an RHI is just staring vertically or making vertical slices of the flow. So what we wanted to do was to compare the in situ measurements with the remote sensing measurements to see if we could learn anything about how good the remote sensing estimates were, as well as what is actually happening in complex terrain. So sometimes it's more fun to look at a pretty picture. So I was very grateful that Norman brought drones to Perdigäo and could take these beautiful scenic views of our instrument site. But you'll see that the wind turbine is over here. This is the blimp for the TLS. And there's a little line coming down here to the base station. The probe is probably right there. Then we have towers. There's another tower over here. And then the 2 lidars, this one and then another one that would be right here, staring at the domain. So we're going to look at dissipation rate estimates from all of these instruments. It's nice to have a sense of how much this field has changed in the past 3 or 4 years. If I was in the audience, this would totally be a slide that I'd be taking a picture of, so I don't mind if you do that. But people have been looking at many different ways of using different types of scans from lidars to estimate turbulent quantities. All of these approaches have their limitations that are very well described in the papers that discuss that approach. So here, we're going to be focused on using vertical stairs. Nicola built on some work that Ewan O'Connor did back in 2010, and then Norman expanded one of Smaliko's methods to use RHI scans to estimate dissipation rate. So when you do planar RHI scans, you usually have one lidar staring at another lidar, and they're both making vertical slices, and you want to compare the information from one system to the other system in order to create a full picture of the flow field. And that's what we see here. We have full flow fields of the mean winds, both on top and on bottom, and these are just 2 pictures from different times of day. And when you do that, you have a really good sense of what the velocities are as long as the flow is aligned with your lidar measurement beam. What you don't have is a way of getting good turbulence measurements just from these combined scans. So you can combine the data, you can interpolate them onto a grid, you can get the 2-dimensional flow in the direction of the lidar alignment. You tend to have to average that over a relatively long period of time, which is unfortunate if you care about turbulence, because that doesn't really give you anything that you want. So we have to work on another method for getting turbulence. That's interesting. I'll just go ahead and add all of that in. Okay, so what the approach that we're taking, or that Norman identified, building from Smaliko's method, is to take the line of sight velocity variance and the broadening of the turbulence spectrum from the lidar returns, and to use those along with some quantities that are integral to the way that the lidar itself is operating, and to use those to get from the line of sight velocity variance, include the turbulence broadening, and include a shear contribution, include some features of the lidar itself, and use that in order to estimate the actual variance, so not the measured variance, but the actual variance. And once you have that, and we have a parameter fit for this length scale, then you can estimate dissipation rate. So Jim, I was actually thinking about you when I put this slide in because I knew that you'd be excited about this. The idea is that we have the measured variance here, we have the turbulent broadening of the spectrum there, and then everything under this red line contributes to the total variance. So this is the approach that you end up taking, and again, this is building off of Smaliko's work before. So this is not a very interesting thing to talk about in a seminar, but I thought that it would be important to show it. What's even more exciting is to compare the RHI-based estimates of dissipation rate to what we have from the tower measurements at the same altitude, slightly offset in space. And so what we see here are the shape of the dots tell us which lidar gave us the measurement, and then the colors tell us the probability density. And the R value is around 0.78, so that's certainly not perfect, but it's much better than any of us had expected when we were going into this. Similarly, we can compare the method that Nicola used to use with a vertically staring lidar, and we can compare that to the tower measurements as well. We have much more data because we weren't trying to coordinate scans. This lidar was just staring vertically the whole time. And again, that agreement is pretty similar, around 0.8. Okay, so now that we have that, we can start to look at particular events and particular case studies. So this is an exciting case of a southwesterly nocturnal low-level jet. So southwesterly flow is important because that is perpendicular to the ridge, and it has inflow coming into the turbine and gives us the opportunity to maybe, possibly see a wake. And once we do that, so this is the RHI estimate of the mean flow, and this is the estimate of dissipation rate from one of the lidars, and this is the estimate of dissipation rate from the other lidar. So there's a lot going on in these pictures. So first, I want to draw your attention to the low spot in the valley. This is a location where the clamps lidar was based on the ground and staring straight up. So you see these boxes, those are showing the estimates of dissipation rate from clamps. And then you have this kind of tilted profile. Those are the measurements of dissipation rate from the TLS, from the measurements on the balloon. And so when what is inside the box matches what's outside the box, we can say that we have good agreement between the in situ measurements and the remote sensing measurements. You might also be wondering, why are there so many gaps? What's all that white space? That white space is incredibly annoying, but it's happening because we have very low values of dissipation rate, and we can't actually distinguish the real dissipation rate from, or the signal from dissipation rate from the noise. And you see that we have more cases of that for this LiDAR, and that's because that was located further away from the source of generating turbulence. So we have more data down here. So we can start to look at some of the details and think about, there are very large values of dissipation rate close to the ground. Okay, we can check off that that matches our conception of the world. That's what should be happening. And we can also see that we seem to have very large values of dissipation rate downwind from the turbine. And we're going to look at that in a little bit more detail going on. All right. Was there anything else I wanted to say here? Oh, right, yeah. The really important thing is to note that we have this nice, beautiful, strong low-level jet. And within the body of the low-level jet, we seem to not have very much turbulence. It's very laminar flow. But above the low-level jet, where we have a lot of shear, we have a lot of dissipation. So this also matches our view of what we would expect, that when we have a lot of shear, we have increased production of turbulence and therefore increased dissipation. Okay, we can also look at vertical profiles from all of these instruments. And so this is where the strength of Perdigäo comes in, because we have one line for the tethered lifting system. We have the red lines that are dashed and dotted. Those are estimates of dissipation from the DLR lidars. The blue line is the estimate from the clamped system. And then the black dots are tower measurements. So 0 is the elevation of the base of the turbine, or the ridge top. And so what we can see is that at the ridge top, we have dramatic changes in the values of dissipation rate. So near the surface, within the valley, we have very small values, but then it rapidly increases within the valley. And then we again have a decrease up here. We also have some very strange disagreements further aloft, and this is up near the altitude of the top of the low-level jet. So that's interesting to explore. I also want to point out that these are at 2 different times, and so we have evolving flow phenomena that let us think about what were these instruments actually seeing. Was there anything in the domain that, given changes of wind direction, could we be seeing some interesting phenomena like the wind turbine wake? So that's what we see here. Here we're looking at a time series of dissipation rate from the suite of instruments that I was just talking about. And here we have wind direction. 2 of these wind direction bands are highlighted in particular. One of them is where the DLR lidars are expected to be in the wind turbine wake just based on the wind direction. And the other one is where the clamps lidar was expected to be in the wind turbine wake just based on wind direction. We can also see that the wind speeds at the ridgetop tower are very different and much stronger than what was happening at the valley tower. And we can see that in general, at a given altitude, and I believe that this is at 100 meters above the surface, at a given altitude, there tends to be pretty good agreement between clamps, the TLS, and the TLS was being raised and lowered over the course of the night. So we only use the data that was appropriate between 90 meters and 110 meters. So we tend to have pretty good agreement, except for certain time periods that may have a connection to the wind turbine wake. So in particular, we'll look at that one.
So,
Yeah.
are you making an assumption that the turbine wake is actually parallel to the incoming wind direction?
Yes, we are making.
There's no lateral shift
Yes.
in the position of that wake or being exposed to the valley flow up and down?
So once we're assuming that the wind turbine wake is advected directly into the valley at this location, there are reasons to think that maybe after it's gone halfway through the valley, it should deviate in one direction or another. But this wind turbine was not operated in a way where you would expect that the wake would be steered in a different direction. So you can steer wakes, but that it requires a lot of computational knowledge and intentional work. And we know that that company was not doing any of that related work.
But I'm more thinking of it, the wake as a passive feature. It's a deficit of momentum. But but once it enters it's in the valley, it's exposed to the valley circulation as well.
Yes, yeah, once it enters the valley, it would be exposed to that. Yeah, and we'll look at how we can see it enter into the valley and how it changes as it goes down the side of the slope. Yeah. Okay, so here are some profiles to assess this behavior. So now we have orange measurements, and these are the virtual towers that are created by having this lidar and that lidar staring at these different points in space. So when you have multiple lidars, it's really nice to have software that helps you coordinate so that you have these virtual towers so that you can extrapolate, profiles of wind speed at different locations and profiles of wind direction. So to Vanda's point, we have, if we're well above the ridgetop and well above the turbine, those 4 virtual towers all pretty much agree on what the wind direction is. But as we enter the turbine wake area, we can see that there is a rotation of wind direction depending on how far downwind you are here. But since we did not have perfect scanning LiDAR measurements of the wake at the time, it would be very difficult to assess exactly where it was, which is why we've highlighted those bands, because those are approximately where we would expect the wake to be. So in my other work, when I've looked at wake meandering, in these types of stability conditions, with this type of terrain, I wouldn't expect meandering more than 5 degrees or so. But again, we don't know. So clearly we need more lidars, and it would be great if EOL would buy more lidars so that we can do this for Perdigäo round 2. All right, okay, where was I? So we want to think about stability as well, and this is a nighttime stable case. We can see from the green profile, this is a radiosonde launched from, again, the valley floor, which is interestingly 10 meters above our TLS base, and the temperature gradient, as you were walking from that base up to launch a sonde in the middle of the night and then back down, that was a pretty significant temperature gradient at times. But the important point here is that we have a stably stratified inversion well above the ridgetop. That's confirmed with the TLS measurements in Burgundy as well, and with the tower measurements also. Okay, so we have that. We have the situation where we have the evolving wind direction. And so now we can look at individual RHI scans. So these are no longer the 30-minute scans. These are more or less instantaneous. So this is an estimate of the horizontal wind speed from the 2 lidars looking at each other. We have what seems like incoherent flow immediately behind the turbine, some small accelerations going down the slope, and then again, more nonsensical patterns here. But that is characteristic of what we would see of a wind turbine wake that is indeed rotating slightly as it propagates down. What's even more exciting to me is to look at the estimates of dissipation rate over here on the right. So this is from one lidar on the top and the other DLR lidar on the bottom. And again, the yellow warmer colors represent higher values of dissipation rate. And we can see that there are these strong increases of dissipation rate coming down the terrain and then popping back up again. They are not directly connected to the terrain. So we would normally expect to have very high dissipation rate very close to the surface if it was just a normal flow with nothing else going on. So that one of the reasons why I think that this is the wake is that we have something that looks like it's kind of bouncing down on the bottom of the valley wall and then bouncing back off. And so we have this zone of smaller dissipation rates here. Further, these are pretty large values for just topographic flows. We do have nights where there was no wake being generated, but those are also nights when the wind speeds tended to be lower. So we don't have a perfect control comparing wake on and wake off. What we can compare to are other measurements that we've made in the wake of a wind turbine at NREL. And so there, our values of dissipation rate measured much closer to the turbine, measured more like right here rather than down here. Those values were significantly larger than what we see here. So these values are not inconsistent with the idea of a wind turbine wake, but they're not as large as what we've seen in other locations. Jim? These were 5 to 5:30 UTC, which is an hour off of local standard time.
In local time?
Local time, 4 to 4:30. Yeah, you're right, that's the relevant number. Okay, so I hope that I've convinced you that everyone should put pressure on Vonda to buy more lidars so that we can do measurements like this, and that we can learn some things about turbulence dissipation rate using new methods that are continually being developed to use these new instruments to the greatest capacity. And I wanted to quickly touch on some large eddy simulations that Tina Chow and her students are doing at Perdigäo. And this is just a quick movie. This is WRF LES driven with mesoscale conditions. There is a turbine located in these simulations, and this is just a slice of wind speed from the WRF simulations. There's much more interesting stuff going on here, but I wanted to show you that we have an actuator disk parameterization in WRF LES. And so we can see zones periodically of slower wind speeds plopping down as the wake is intersected with this vertical slice. So there's a lot of ongoing research in improving the actuator disk model for use in complex terrain. There are some interesting things about the way that it functions. But this is the motivation for the next thing that I'm going to talk about, which is how do you actually compare model results to scanning LiDAR measurements in complex terrain, because we want to take advantage of all the data that we have here at Perdigäo. So the idea of implementing a LiDAR simulator is not new. People have been doing these types of studies for many, many years. With some of my projects at NREL, we did a LiDAR simulator for a profiling LiDAR so that we could understand if we generated a wind turbine wake and if we put a profiling LiDAR in different locations in the domain, what would our error be? What would the difference be between the red line and the black line over here in terms of what the LiDAR would think it was seeing versus what the model predicted was actually happening. So we're building on this idea, and we're implementing our LiDAR simulator into WRF LES because that's the model that we're doing for our studies. So Rachel Roby is a graduate student working with me on this, and she's right now doing the outside of the code demonstration where she's got different wind profiles, a linear profile, a log profile, a low-level jet profile, and making sure that as she's implemented the range gate weighting function, which is really important to include. Back on this study, we found that when we implemented the correct range gate weighting function, we had very different results. So she's working on implementing that. She has scan geometries and scanning rates that will be determined by a nameless file, and she's thinking about PPIs and RHIs and VADs. So that's ongoing work, and we have submitted an abstract to the BLT meeting in July, so that is my best guess for when that will be finished. My optimistic guess. She's an amazing student, so I'm sure it will be good. So I should summarize here by just pointing out that we had many, many institutes working together, led by EOL, to make sure that we had all the data archiving, all the instruments working properly. EOL did a tremendous job. We blanketed the Valley with all sorts of sensors and airborne measurements, and we've learned things that help us improve our modeling capabilities. The next step for developing the new parameterization is still to come. And then the fact that we were able to have so many instruments in such a small area lets us quantify agreements between in situ and remote sensing observations so that we can get new insights into turbulence and turbulence variability. So I will thank you all for your attention and thank EOL again for the amazing job that you did. And then I have a bunch of pretty pictures if you want to look at that.
Hi, Julie.
Hey, Peter.
Just a couple random thoughts, I guess. Real dissipation is really, really intermittent, and especially when it's stable. I guess, let's say you took the sonics and you averaged over a shorter time. You didn't say exactly how long you did it. Would that change how you viewed your model results, et cetera?
Yeah, so that's a good point about the averaging time. I'm trying to remember now what we ended up using. I do know that we looked at some sensitivity, especially for the TLS, about the averaging time. And I think we ended up settling on something extremely short because especially for the TLS, because it was going vertically through different layers of the atmosphere. So that was really short, but I don't remember what Nicole used for the sonics on the towers. And so we do have uncertainty quantification in this, but I don't remember if averaging time is part of it. So
When you say short, what is short?
for the TLS, we ended up using 30-second intervals for some, because it was rising and lowering at 3 meters per second on some cases. So that was really short. Hey, Don.
I have a couple questions. The first is, why did you use the structure function method rather than the spectral method for dissipation?
Yeah, I had similar questions because it's a lot more computationally intensive. But a good colleague of ours, Domingo Munoz Esparza, was looking at dissipation rate calculations at, let's see, I didn't include that here, did I? Yeah, he was looking at dissipation rate calculations at the BAO during the XPIA experiment and found that although using the two methods tended to give similar answers, there was wider uncertainty using the inertial dissipation method. And so he was recommending using the second order structure function method. And so we picked that up and went on with it.
Okay, well, the second question is, you didn't say anything about what the aircraft did. I'm just curious what aircraft were involved and what they measured.
So the only aircraft were the two tethered lifting systems, so I would hesitate to call them actually aircraft. They were airborne sensors. Yeah, initially we hoped that we would have drones, but for many different reasons that didn't work out.
So they were measuring turbulence?
So on the TLS, we were measuring turbulence and then slow temperature and moisture, pressure, wind speed, that kind of stuff. But it was really the hot wire anemometer measurements on the TLS that were important for what we were doing.
Okay.
Yep. But yeah, I mean, it would be great to have drones in the EOL pool as well. You're never going to let me come back and talk again.
So I just wanted to continue the discussion about dissipation rate. I'm not hammering it because I think what you did is not a good thing. It's a great thing, and I think it's a great way to show the wake, for example, of the wind turbine and so on. But all the methods that you're using of necessity, frankly, without actually measuring directly the strain rate and so on, require an assumption of equilibrium. Every method that it uses spectra or structure functions and so on assume equilibrium between the large scales and the small scales, you know, in the flux of energy down the spectrum and so on. And of course, many of the flow regions you're measuring are probably pretty far out of equilibrium.
Yeah.
So what that means is that in the interpretation of the structure function, you know, perhaps you need to sort of define a non-stationary or non-equilibrium parameter of some kind to sort of say these are regions where we have more concern than other regions.
Yeah, and absolutely. And so that's why we have the error quantification in Norman's paper. There's a whole section about that that includes how we would calculate that, why it's large in some areas, why it's smaller in other areas. And let's see. It was in AMT at the end of this year, or at the end of 2019 or the beginning of 2020. But for the purposes of a seminar, I wasn't going to go into we trust this and we don't trust that. So this case study is the one that we highlighted in the paper because we were relatively confident about the values that we were showing, especially where we're comparing the in situ measurements to the remote sensing estimates. But yeah. I don't know if you were our reviewer or not, but that error quantification section was very detailed. Okay. You didn't see it? Well, you should go see it now. Let's see. Okay. Well, this is as close as we'll get. Buildman et al.
I should preface my question that I'm not trying to get more arguments for buying more lidars. So,
Noted.
but my question actually originates with your first animation you showed us of a stable case and an unstable case, and comparing the wake in these two. If you can bring that back while I'm formulating my question, that would be great. What I noticed
of the
there-
turbine wake?
Of the turbine
Yeah.
wake in your Perdigäo overview. What I noticed there is that actually there was a region of turbulence really close to the ground, even before, right there. So you start looking at the turbine wake, but that one is merging with something that is actually happening right there close to the ground.
Mm-hmm.
So so the question is, do you have a cross-section with the LiDAR data and the tower data that you can analyze doesn't contain the turbine wake, so that you get only the terrain-induced turbulence?
Yes, we have many different examples of RHIs encountering the turbine. Whether or not we have wind speeds that are high enough to match to this without the turbine being on, that's a different question.
Because what I think you are seeing in that turbine wake is actually a combination of the turbulence generated in the wake of the turbine, plus the separation, in the boundary layer related to just flow over complex terrain. And so that actually speaks to the point, how stationary, whether these flows are in balance or not. Most likely not, especially when you have separation close to the
Yeah, so that echoes, that's a really good point, and that echoes back to the need to be able to extend the measurements with modeling studies. Because in model world, we can easily turn the turbine on and off and assess the topographically driven turbulence, whether it's from flow separation or something else, and just, terrain roughness, or if it's really due to the wake. And so that's
sort of a null cross-section where you don't have a turbine. So the one that's parallel to that one.
Yeah. So we don't have a LiDAR scan that is null because the topography of this double ridge valley is not as perfectly symmetric as we would like, but we can do that in model world and are planning to do that. Steve?
And you, of course, have the other transect.
We have other transects, but again, as Robert showed, whether the valley is deeper or more shallow, that changes the way that the flows respond. So it's going to be different.
You might see the recirculation zone in the same case.
Yeah, maybe, yeah.
Julie, when you did the machine learning,
when Nicola did the machine learning, yes.
when the machine learning was done,
Ellie, get used to the passive voice.
I saw that L had a really small effect.
Yeah, I was disappointed.
Does that have I would have initially suspected that L would really matter.
So did I. I was disappointed and asked Nicola several times, did you, recycle through all the data points? Did you do this? Did you do that? And to the best of what I could understand and the best of what he can see, it's really more of the turbulence where, L is going to help predict the turbulence, but it's really the magnitude of the turbulence itself that exerts more control over dissipation. So I think that this is similar to other problems where we think that stability is the main driver, but stability drives the generation of turbulence. And turbulence is the thing that's interacting with whatever we care about. In this case, it's dissipation. In other cases, it can be diffusion of a concentration. So it's really the turbulence that matters, and I think that that's what the machine learning is telling us. Yeah, that's driven by stability to some extent, but it's really the turbulence that's doing the pushing. I'm guessing. That's how I'm making sense of it myself.
Okay, then just to follow up, I'm wondering, is this primarily close to neutral flow? Could that be why L is not so?
Oh, no. No, there were very strong variations of stability here.
Okay, so like the mean wind wasn't that strong typically?
The mean, I don't have a good number off the top of my head, but I remember seeing very large heat fluxes and very rapid cooling at night. So I think you're suggesting that if the winds were strong enough, then that would push us into neutral. I don't think that they were that strong because I don't think that the turbine ever got past region 2. So that means that the winds at the turbine level would have been 12 meters per second or below.
Can I just ask, what is causing the reverse flow in that left figure above? And it's got such a sharp interface between the blue and the red.
Yeah, it's not really
negative.
reverse flow. It's just that the wind, I don't remember if it's this way or that way, but the wind is actually veering with height. And remember, we're only getting along the LiDAR line of sight. So say that this is more southerly and that's more northerly, and the main component of the flow is not really being sampled by the LiDAR wind speed.
So it's not really reverse flow.
It's not really reverse flow. It's fun to think about, though.
It's weird.
Well, I think LiDARs are a really good teaching tool also for thinking about flows and developing intuition. Right before I came over here, I was teaching wind energy meteorology about how LiDARs are wonderful. And it's the same thing. Students get a much better physical sense of what's happening when you can see it.
with more questions?
In that image on the left, there seems to be an artifact.
Yeah, so the artifact coming up here, yeah, this is probably due to an obstruction along the LiDAR line of sight. So if you have a tree branch that comes in and out of the beam, then you can get something that looks like that. Yeah, I keep meaning to ask for an updated and cleaned up version. It's easy to remove those just based on the signal to noise ratio, but this is one of our early results and it tends to generate a lot of discussion, so I included it.
Yeah, so if we don't have more questions, then let's thank Julie again.
Thanks for your attention.